When analyzing complex graphs like routing tables or social networks, the challenge is finding a reliable way to isolate and group disconnected data points. To run advanced algorithms on these structures, we first need a strict mathematical framework to define those boundaries, and that framework relies entirely on sets. A set is a collection of distinct elements. Here, integers 1 through 4 form a valid set. The first essential property is element uniqueness. When a duplicate value attempts to enter, it is rejected. Sets store each element exactly once. This uniqueness prevents algorithms from getting trapped in infinite loops. The second property is order independence. Shuffling the arrangement to 3, 2, 4, 1 yields the exact same mathematical entity. An equal sign proves their equivalence. This marks a sharp departure from standard computational arrays. In a true mathematical set, index positions are irrelevant. The only detail that matters is whether an element exists inside the boundary or not. By enforcing strict uniqueness and discarding sequential order, sets provide a perfectly deterministic foundation. They give algorithms highly predictable data structures to work with. Once data is organized into sets, a computational system needs a systematic way to compare or combine those separate groupings. The first primary operation is the union, which executes the complete combination of all elements from two sets into a single structure. Above, then circles A and B merge to represent the union. Below is the programmatic logic. A union requires a for-each loop iterating through set B. The system checks if an element is absent from the result before appending, preserving the uniqueness constraint. If union is about expanding combinations, the intersection operation does the opposite. It extracts only the exact elements shared between two sets. Here, circles pull apart, leaving the center overlapping wedge highlighted. The corresponding algorithm iteratively checks set A. An element is only appended to the final array if it mutually exists in set B. Union operations expand data boundaries while maintaining integrity, whereas intersection operations tighten constraints to find mutual truth. The third operation, difference, isolates elements that are unique to a primary system by explicitly subtracting any commonalities found in a secondary system. This shows set A minus set B. Only the non-overlapping left crescent remains. Difference is strictly asymmetrical. The negative constraint inside the loop isolates elements exclusively from the first parameter. A minus B yields a completely different result than B minus A. We verify these operations using set A 1, 2, 3 and set B 2, 3, 4. Union merges them 1 through 4. Intersection extracts shared values 2, 3. Difference proves asymmetry. A minus B leaves 1, while B minus A yields 4. Mastering these three atomic operations allows developers to programmatically mutate and isolate any grouping of structured data. This raises a specific architectural question. What occurs computationally when an intersection operation finds absolutely zero common ground between sets? When there is no overlap, the output is the empty set, representing a mathematically null state. This condition defines disjoint sets. Two sets are disjoint if their intersection strictly results in the empty set. They share nothing. Real-world data is rarely limited to two isolated components. When mapping complex networks, we map an entire family of disjoint sets. A family of disjoint sets ensures that every distinct piece of data belongs to exactly one specific group, with zero crossover or data bleed. Achieving this mathematically verified disjoint state is the precise mechanism required to prove total isolation between system components. We can map this mathematical framework directly onto the programmatic reality of graph architecture. Disjoint circles become isolated node groupings. Separated clusters in a computer network, or communities in a social graph, are simply families of disjoint sets. The premier application is Kruskal's algorithm for finding minimum spanning trees. It relies heavily on disjoint sets for cycle detection. When connecting two nodes, Checking their sets verifies if the edge safely merges separate clusters or invalidly loops back. To reach this point, we defined the strict axioms of a set, mapped the atomic operations, and established the empty set as the basis for disjoint verification. However, pure mathematics has a programmatic limitation. While set theory perfectly describes data, standard array implementations are too slow to run these dynamically at scale. This latency requires a highly efficient architecture designed to manage disjoint families in real time. That architecture is the union-find data structure, the optimal algorithmic tool for managing graphs, and the exact objective of the next module.